Hi, in this video I will be talking about dienes, specifically conjugated dienes, and why they are more stable than non-conjugated or isolated dienes, and how we know that they're more stable, and then also some theory about why they're more stable. So let's start with how we know that a diene is more stable. Let's do a couple of experiments that have been tried in the past. What would you expect to get if you were to do a dehydrohalogenation on, what would that be, 4-bromocyclopentene? And let's use our old familiar alcoholic KOH. What products could we expect to get, and which is the major product? Well, it turns out we might expect to get the bromine and the hydrogen coming off of these two positions and put the double bond in there. Remember, this is E2, so there are no rearrangements. Or we might expect the hydrogen and the bromine to come off these two carbons, and we would expect to get that product. In fact, we only get one product, or at least the vast majority of it is just one product, and that is this one. That suggests that this is a more stable compound than that, since we only get this product, or at least mostly this product, and not much of any of that. Well, notice that this is double, single, double, conjugated. This is double, single, single, double, non-conjugated or isolated. And that is one experiment that suggests that the conjugated diene is the more stable one. Furthermore, if we can measure what's called heat of hydrogenation. Now let's just do a little background on what is heat of hydrogenation. Well, as you know, if you take an alkene and add hydrogen to it, usually requires some sort of a catalyst like nickel or palladium or any other of a whole number of fancy catalysts, but nickel usually works just fine. You will get an alkane. Turns out that the delta H for this reaction, or this type of reaction, is always a negative number. In other words, it's exothermic. So we can do that on various alkenes, and we can measure what is that delta H. And as long as the two alkenes that we're comparing will give you the same product in the same product of hydrogenation, we can use that to determine which one had more energy to begin with. In other words, which one is more stable to begin with. As an example of a reaction that you are familiar with and that you can probably predict, let's take a simple alkene like 1-butene and compare it to 2-butene. In both cases, we will add hydrogen with a catalyst. And in both cases, we'll end up with the same compound. And that's important, that if you're comparing that you're getting the same compound, but different starting materials. Okay. Well, what about the delta H's of these reactions? This is what's called the heat of hydrogenation. In both cases, it's going to be quite a big negative number. Again, exothermic, just like we saw in the generic example a few minutes ago, but not exactly the same delta H. Which one would you expect to have the greater negative, or the more negative delta H? Well, which one of these is higher energy to begin with? Your understanding, I hope, of alkene stability is that the more interior it is, this is technically called the Zaitsev rule, the more interior alkene is more stable, meaning this is lower energy than that to begin with. So if this molecule is lower in energy than this molecule, again, more stable because more interior, therefore lower in energy, if this is an energy diagram. And in both cases, we're going to hydrogenate, and we're going to go to the same compound, being butane. And butane has the energy much lower. Which one would give a bigger negative heat of hydrogenation? This one, which is downhill, or this one, which is even more downhill? Well, the answer obviously is this would be a bigger negative number and therefore that's a less stable molecule to begin with. So essentially what we can say is if we're comparing two alkenes, when you hydrogenate them, the one that gives more energy out, in other words has a bigger negative at delta H, is the one that's less stable to begin with. Okay. Well, we can use that exact same idea, and we can start with two alkenes that will give us the same product. In this case, it's going to be dienes. So it turns out if you start with 1,3 pentadiene as compared to 1,4 pentadiene, and we hydrogenate both of those. Now notice these are both dienes, which means they're both going to require 2 hydrogens, and that's also important that if you're comparing them, that you have to add the same number of equivalents of hydrogen in both cases, because the hydrogen itself contributes some energy to the reaction. But the fact is both of these will give the same product. Which is pentane in both cases. And these have been measured, and I happen to write down the numbers. It turns out the heat of hydrogenation of this compound, the delta H, is negative 226 kilojoules. The heat of hydrogenation of this one, the non-conjugated one, is negative 254 kilojoules. Therefore, this is a bigger negative heat of hydrogenation. Therefore, this must have been higher in energy to begin with. Both to give pentane. Again, going down to the same starting material so that we can be guaranteed that it's not the starting material, but it's the product that's affecting the delta H. It's just the energies of the starting materials. This one downhill from the conjugated one, that's this one, negative 226. And from the non-conjugated or isolated one, negative 254. Clearly, that must have been higher energy to begin with, and therefore this is the more stable. Again, the conjugated double, single, double is more stable than the double, single, single, double. Again, that's just a way that you can measure the difference in energies, and from that infer which one is the more stable of the dienes. A similar result is obtained from cyclopentadienes 1,3 versus 1,4. And I won't put the numbers up here, but just to give you a rough idea, comparing 1,4 and 1,3 cyclohexadienes, this one is higher in energy than that one by a matter of about 1.6 kilojoules. Not nearly as big a difference as in those other ones, but still, this is higher in energy than that because this is conjugated double, single, double, and this is not double, single, single, double. Okay, so essentially what we've done at this point is several different experiments that show unequivocally that conjugated dienes are more stable than non-conjugated dienes. Now what we'd like to do is understand why that might be. And we're going to use each of the 3 models that we talked about in an earlier video. In model 1, let's review. Model 1 involves Lewis dot and resonance structures. Model 2 involves overlap of atomic orbitals. Or for short, AO, kind of an abbreviation that chemists use for atomic orbitals. And don't forget, atomic orbitals include S, P, D, F, and so on, as well as hybridized atomic orbitals, sp3, sp2, sp, those are all atomic orbitals. And then model 3 is the more complicated but often more useful molecular orbital. model. Or MO for short. Okay, so what we want to do is look at a conjugated diene. That is double, single, double. And let's just do the very simplest one we can, which is 1,3-butadiene with all hydrogens attached. That way we're limiting the number of atoms we have to worry about and the number of sigma bonds. So this is the Lewis dot structure. Can we use this by itself to explain why a conjugated diene of double, single, double is more stable than a non-conjugated? And the answer is yes. We can actually draw another resonance structure for this, actually a couple of other resonance structures, in which we simply move the double bond to a different position in the molecule, keeping all the hydrogens and all the carbons in the same place, because remember when you're doing resonance structures you can't move any atoms, so hydrogens and carbons are all in the same place. All I did was move this double bond down to that position. In order to not have 5 bonds of that carbon, now I have to move a pair of electrons out onto that carbon, and it then becomes negative. And similarly, this one has lost a pair of electrons as we moved it into the double bond in that position, and so that ends up with a positive formal charge. Okay. Now, how do you like that for a resonance structure? Not great, right? Because it has a carbon without an octet, and furthermore it has charge separation. So this is not a very important resonance structure compared to this one, but it is a resonance structure that you can't draw a similar one in the case of a regular alkene. Furthermore, we can just shift them the other way, and we can have another resonance structure in which the carbon at this end becomes negative, and the carbon at the other end is the carbocation, and it becomes positive. And then, of course, since these two are resonance structures of that, they're also resonance structures of each other. Now, I'm wondering, probably some of you are thinking, now wait a minute, Dr. Armstrong, these two are the same as each other, just turned around, so are they really two different resonance structures? And the answer is yes, they are. Remember, what we're assuming is that we're freezing these in space. In other words, you can't move atoms, so you can't take this one and turn it around in order to become that. Essentially what we're doing is taking a snapshot of the molecule at any given point in time, and we're seeing how many different ways can we arrange the electrons within that molecule. And so part of the time this is a neutral carbon. No, I'm sorry, I shouldn't say part of the time, because remember it's not jumping back and forth. What we should say is part of its aspect this is a neutral carbon, and part of its aspect it's positive carbon, and part of its aspect it's a negative carbon. Furthermore, this is a single bond in this resonance structure, but it's a double bond in both of these resonance structures. Now, when we can get a handle on how important are those resonance structures is by looking at the length of this bond and seeing if it's really more like a single bond, or more like a double bond, or somewhere in between. And the answer is it's obviously somewhere in between, but it's actually more like a single bond than it is like a double bond. And that's because this is a more important resonance structure than either one of these two. Nevertheless, it is shorter than a normal single bond, and that's because it has significant amounts of contribution from each of these two resonance structures. So, overall, what we can say is that, and here's the general rule, you've heard me say this before about resonance structures, the more resonance structures you can draw, the more stable the molecule is. And since we can draw these resonance structures, that suggests that it's a more stable molecule than it would be if we couldn't draw the resonance structures. So that's model 1, essentially saying we can draw more resonance structures. What does model 2 show? Well, model 2 is the one where we look at overlapping atomic orbitals. Now what I'm going to do is take a little shortcut and not draw all the sigma orbitals, the sp2s and the s's and all that. I'm just going to draw those as dashes to show the sigma overlaps, and you know you could draw an sp2 this way, and an sp2 this way, and an sp2 this way, and show s's stuck on the ends and put in pairs of electrons and so on. But all we're really interested in here is the extra p orbitals, the leftover p's that are 1 at each of these 4 carbon atoms. Okay. Now the reason that we draw those is because in the original compound this was a double bond, and so these two overlap to form that double bond, and this was a double bond, and so these two overlap to form that double bond. But notice, if there's only a single bond in between, then these also overlap. And so the 4 electrons that are in there, let me use red to be consistent. One electron in each of those 4 orbitals. Where are those 4 electrons localized or located? And the answer is, this one is actually spread out over all 4 orbitals. This one's spread out over all 4, and so on. So these electrons are what are known as delocalized. They are not stuck on 1 or even 2 carbon atoms, because of course in a regular alkene, each of the electrons is in both p orbitals at the same time. But in a conjugated diene, they're even more delocalized. They're spread out over 4 carbon atoms. Here's another general rule. It's sort of similar to the resonance structure rule I mentioned a minute ago, but generally what we have discovered is that the more delocalized the electrons are, the more stable the molecule. So there's something about delocalization that makes molecules stable. Now neither of those rules of thumb, that is the one that says more resonance structures gives more stability, or the one that says more delocalization gives more stability, neither one of those really has a good explanation as to why. It's just been noticed over the years that if you can delocalize or if you can draw more resonance structures, that tends to produce more stable molecules. In order to explain that, we really have to look at the molecular orbital diagram. So let's do that now. I will redraw the original butadiene molecule so we can get a rough idea of how many, well, not a rough idea, an exact idea of how many sigma orbitals there are going to be. And remember, what we do is we count for each sigma bond, there's going to be 2 orbitals, thus two atomic orbitals, an s and an sp2, or an sp2 and an sp2, but 2 atomic orbitals, therefore 2 molecular orbitals. That will translate into a sigma and a sigma star, sigma down at the bottom and sigma star at the top. So how many sigma bonds are there in this molecule? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigma bonds. Notice I counted 1 from that, because remember double bond is 1 sigma and 1 pi. So a sigma and a sigma plus all the rest of them is 9 sigma bonds. Therefore, 9 sigma orbitals at the bottom. And some of those are sigma s, sp2, some of them are sigma sp2, sp2, but they're all basically just sigma orbitals. And then we'll also have 9 sigma star orbitals at the top. Okay? But don't forget, we also have a p orbital at each of these carbons. In other words, a pi bond here and a pi bond here. That's going to give rise to 4 more orbitals. Those are going to be called pi orbitals. We saw that for an alkene, there are 2 pi orbitals, and they're arranged pi a little bit lower and pi star a little bit higher. Well, what happens if we have a conjugated diene? What happens then? Well, what happens then is that you get 4 new pi orbitals, but they are arranged in a stair-step fashion. And so we have 4 new molecular orbitals in the middle. The lower 2 are called pi, and the higher 2 are called pi star. Okay. Now maybe we should see if we can see what would those pi orbitals look like, and why are they arranged energetically, bang, 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 like a 4-rung ladder. Well, what we're going to do is look at the possible ways you could arrange those 4 p orbitals. So here are my 4 carbon atoms, and here are my p orbitals. And don't forget, each one of these could be plus or minus, top or bottom. So those are all various ways that they can be combined, plus, plus, minus, minus, or plus, 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 or minus, plus, plus, minus, and various things like that. So let's say all 4 of them are plus on the top and minus on the bottom. They are going to be constructively interfering, so they're going to spread out over the whole top and over the whole bottom, and we'll end up with a molecular orbital that looks like that. Positive on the top and negative on the bottom. I think that's the first time you've seen a 4-carbon molecular orbital, or a molecular orbital that spreads out over not 1, not 2, but 4 whole atoms, all of which are subsumed by that 1 molecular orbital. Notice that if you put electrons into this orbital, they will pull together these carbons and these carbons and those carbons. So there's a net of 3 bonds that are made stronger. So we'll put a little notation of 3b there, meaning that all three of these bonds, that one, and that one, are made stronger by an electron in this orbital. Okay, so there's one of the four. That one turns out to be this one right there. That's the lowest energy of the four molecular orbitals. How else could we arrange the pluses and minuses here? Well, what if we had plus, plus, minus, minus across the top, and that would force us to have minus, minus, plus, plus on the bottom. Notice then that we have a node right here. In other words, we cross from a positive to a negative at that point. And if we draw that as one orbital, it's going to look like that, and it's going to have an extra node in the middle. And if you remember from our previous video, anytime you add another node into a molecular orbital, you increase its energy. So this is going to be higher in energy than that one is. But what about electrons in that orbital? Will they make it stronger or weaker? In other words, is it a bonding or an anti-bonding orbital? Well, what you need to do is look at each of the three bonds in turn. This one is covered by both carbons are covered by this part of the orbital, and so this bond is made stronger. This one similarly made stronger, but what about this one in the middle? Made weaker. So this only has two bonding and one anti-bonding, and so that's a net of one bond made stronger. So we're going to write 1b for that one. And that then is that pi orbital. It's still a bonding orbital, and therefore it's still called pi, not pi star, but it's not as bonding of an orbital as that one is. Well, let's keep going. What else could we do? Well, we could have on our four orbitals plus, minus, minus, plus, 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 minus. Notice then that there's another node. There's a node through here, between that positive and negative on the top, and another node through there, between that negative and that positive on the top. Or if we draw it as a full-blown molecular orbital, it's going to look kind of like this. Wow, there's a fairly complicated looking orbital. 6 parts to it. Okay? Positive, negative, positive, negative, positive, negative. That's a 6-lobed, 4-carbon molecular orbital. That's a big one, isn't it? It has 2 nodes. And again, we've gone up by 1 energy boost, in a sense, by adding 1 extra node into the orbital. Now if we look at the bonds and whether they're made stronger or weaker by an electron in this particular orbital, this one's made weaker because the signs are opposite on either side of that bond. This one's made stronger, this one's made weaker. So essentially 2 anti-bonding and just 1 bonding. That's a net then of 1 anti-bonding. So that's the next one up in the 4 molecular orbital pi scheme. And that's that one. And notice then that that one's a net anti-bonding orbital, and therefore we put the star on it. So it's a pi star anti-bonding orbital. And then the next one up from that will arise from yet a different arrangement of the phases of these orbitals. Plus for the first one, minus for the second one, plus for the third one, minus for the fourth one, and then bottoms are being forced to be the opposite of that. So notice now we have yet another node in there. As we go from carbon to carbon to carbon to carbon, we go from positive to negative to positive to negative. We switch from one sign to the other, and therefore that's a node. Or if we draw it as 1 molecular orbital, we get 1 orbital with 8 parts. Wow, 8 lobes in 1 molecular orbital. And it has the signs like that, and it has a node between each of those carbon atoms. And again, if we put an electron into this particular orbital, what's it going to do to these 3 bonds? It's going to make that one weaker, and that one weaker. All 3 of them become weaker. We can note that as being 3A or 3 anti-bonding. And that's the 4th and highest energy of the pi orbitals, and that's that one. So there we go. We have not only put them on an energy diagram, but drawn what do they look like roughly in terms of molecular orbitals. Okay, so we're almost done, but the fact is now we need to put electrons in. Where do the electrons go, and how many are there? Well, I've already erased it, but let's redraw the Lewis dot structure just so we can count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Is that right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Where will they go? Well, down here we have, what did we say? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 18 electrons in here. I'm just going to put them on in pairs real roughly. 2, 4, 6, 8, 10, 12, 14, 16, and 18. Okay. And notice that those 9 pairs of electrons correspond to the 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons, or 9 pairs of electrons in sigma bonds in our Model 1 Lewis dot structure. But then we still have 4 more electrons to put in. Where will they go? They will go 2 in the pi and 2 more in the next pi. Amazingly, both in bonding orbitals, none in anti-bonding orbitals. And so again, what we do is we essentially stabilize the molecule by having all of these pi orbitals below the level that they would be if they weren't conjugated. I mean, that's basically the idea of why the molecular orbital scheme explains the stability of a conjugated diene. What it also does, very nicely, is notice that the gap between the pi, which is the highest occupied molecular orbital, and the pi star, which is the lowest unoccupied molecular orbital, that gap is now even smaller than it was for a regular alkene, which means you can use light of even less energy, like a longer wavelength than you would for a regular alkene. And what we're going to find is that the more and more conjugation we get, the more and more pi orbitals get stacked up in between. The closer and closer and closer they get together, and the smaller and smaller and smaller that gap gets between the highest occupied one and the lowest unoccupied one. And so the longer and longer and longer wavelengths you can use to excite from a ground state to an excited state. Eventually, the wavelengths get so long that they actually become visible, and that's why molecules that have many double bonds, double, single, double, single, double, single, double, single in a row, tend to have color to them because the wavelengths required to excite an electron to a higher energy level are much longer, in other words, less energy, photons, longer wavelengths than for non-conjugated or those with only a little bit of conjugation. Now dienes, like this one, that gap is still too wide to be in the visible region, it's still in the ultraviolet region. But the more and more conjugated you get, the closer and closer the middle ones get to each other, and therefore it begins to sneak into the visible region. Okay, that's it for the little lecture today on molecular orbitals and why conjugated dienes are more stable than non-conjugated ones. Thank you for your attention.